here David Brady. Brady is a professor at University. And he, as far as I know, he's PhD from Caltech with Southeast years ago. He was a professor at Urbana-Champaign in Illinois. And several of you have seen his book. Those I took my class. And he works on computational optical imaging. Now he's building a huge multi-gigapixel camera, and I think he's going to talk about that today. So, thank you.
Hey, thanks, Raphael. Well, thanks for coming today. It's great to be here. Actually, I spoke at the last IGERT meeting at Colorado, which I thought was like yesterday, but turns out to be 5 years ago. And so I'm happy that a couple things have happened in the last 5 years that I'll talk about today. So I'm going to talk about terapixel imaging, and I'll talk about what that means in just a minute. This is the outline of my talk. Basically, the premise of the talk is that imaging, the basic concept of what we mean by an image, is about to undergo a substantial revolution. And so I want to introduce that idea by showing you sort of the past concept of what an image was, what we kind of think of an image is in the present, and what we're going to think an image is in the future. I think a lot of the concepts of the way we deal with an image are about to change substantially. To make the future of imaging, we need to change optics. So the second area of the talk is to talk about what the problem is with optics, and basically what the number of pixels you can get in an optical system is as a function of scale, meaning a function of aperture size and system volume. And then I'll give you some examples of ways that we can address these scaling problems that I'll identify for you. And basically there's going to be three strategies, one based on holography, one based on graded index or metamaterials, and one based on multi-scale lens design. I'll only make a brief reference to the graded index approach, and then I'll tell you a little bit about holographic approaches and multi-scale approaches. Actually, my main reason for bringing up the holographic strategy, one is because it's a very interesting idea, but second, underlying the theme of what I want to talk about today is compressive measurement. And I'm actually going to say almost nothing about compressive measurement other than to talk about it in the context of holography. But bringing up the example in holography is an interesting case in point to raise the issue that, of course, we will have to consider on-the-fly compression and compressive measurement in some detail as we make very high pixel count cameras. Okay, so let's start by talking about images. This, of course, is a very famous image. And this is a context of what we mean by an image. You know, in the past, an image was a very beautiful thing created by an artist. That somebody had to go and make this thing, and then you could look at this image for a long time. It didn't actually tell you anything scientifically, right? There's nothing in this image that you would say, gee, I knew that that tree was like that, or I could go into this image in more detail and discover more. Everything in this image came through a person, through the hand of a person, and so everything in it is kind of artificial, and it's not useful as a thing to be studied other than from an artistic perspective. So this is a more recent image, and this one, of course, the interesting thing about more recent images is images become living things. So this is, I bring this one up because this is popular on YouTube, and YouTube, of course, is maybe in some ways the defining feature of what's interesting in YouTube, in images now, that people are overwhelming the world in all this video from YouTube, saying, look, this is an image. Now this image is artistic, right? If someone is showing you something, but there's a lot you could learn from the image by studying it in more detail. You could learn, you could go into this image and analyze it, and this is real things that are being shown. Already with these images, handling of these images is a defining feature in networks around the world. So it's driving information science, just handling these simple, relatively low quality images. So I'm going to leave that image for you. That's Where the Hell is Matt? You can go look online for Matt's escapades going all sorts of different places. But that's kind of the present status of images. Now, what I want to say about that image that's of most interest to me is, as you start to think about it, is that image involves data captured with a certain resolution, a certain color, and a certain frame rate. All of those are set to match human scale. So, the image is recorded in a way so that when you look at the image, it's pleasing to you as a human. It makes sense to you in terms of the context in which you normally encounter the world. It's at 30 frames per second because 30 frames per second is the rate at which you can process the world. And it has RGB color because RGB color is the way you process the world. It's been a struggle with digital imaging to get to this point, to get to the point where images match human perception. But we're now about to go past that point, that we will make digital imaging systems that vastly exceed human capability. And so the interesting question is to say, what will imaging mean when we can make cameras that, first of all, will capture environments as though you were there. It can capture all the information you could see in an environment, not just where your conscious attention is, but also will capture detail that goes beyond anything you could see in an environment. So I have sort of backup slides, but since I got the network working here, I thought I would show you sort of a glimpse of what I think the future of images is. This is an image, and this is not even a particularly aggressive one, but this is an image of my research group at Duke. And this is a 100 megapixel more or less image. Now you can't tell that it's a 100 megapixel image because it's on a megapixel display, so you could say, why would we capture a 100 megapixel image if we're only going to show it on a megapixel display? And of course, people can only see a few megapixels at a time. So the only way to know that this is a 100 megapixel image is that I can take it and I can zoom. If I can get that thing to go. I zoom and then I'll have to wait a minute actually, especially watch down here, it takes a minute for the image to catch up. But here, because it's a megapixel image, it's on a megapixel display with 100 megapixels, I have available to me 100x digital zoom with maintaining good resolution. So that, in my sense, is what I think the future of imaging is, that there's no sense, now we have this sense that in this kind of image, I can show you the image, but with this kind of image, I can show you the image in one way. I can zoom in, show you more of the image. I can zoom in, show you more of the image, even to the level of scene that I hadn't shaved on that day. And I still have, reasonable kind of detail. So an image becomes something that can never be shown on a single display. Images all become interactive, dynamic things. They become data sets that have to be mined. And so this is what I think is fundamentally going to change imaging, that you no longer have any sense that you can just hang an image or show an image, and as you consider this kind of image in video data streams, you're going to have enormous data sets, and every time you look at the image, every time you work with it, you'll see something different. Multiple people will experience the image in different ways and look at it in different ways, and you'll never exhaust the ability to sort of dig into and interact with these things. Now this particular image was recorded with a trick. So any sensor system really is we're interested in imaging systems, and so you say, well, what's the difference between an imaging system and other kinds of measurements? An image measures a signal that's distributed on a space, so it's an ordered list, that the pixels in the image exist relative to each other in some ordered space. And so when you characterize this kind of measurement system, you're interested in the size of the space that you measure and your resolution over that space. So in this case, you have the field of view defines the size of the space, and your instantaneous field of view or pixel size determines your overall resolution. Now the ratio of those two is going to be the information capacity of the image. How many total pixels did you measure? So the interesting question in optics, of course, is how much information can you get, and how can you, how much, you normally have some balance in trying to consider the range of the image, how big a field of view you would get, for example, and the resolution. Currently in imaging systems, for most systems in optics, you can have a telescope, you can have a cell phone camera. All of those systems end up with a total information capacity around a megapixel. Maybe 10 megapixels, maybe 100 megapixels, but it's not terapixel, and it doesn't go far below a megapixel. So there's interesting questions to ask why that is. Why is it that most systems currently have fixed information capacity, and what the limits of the information capacity should be? If you think about how much information would you like to measure, You know, if you could measure everything, of course this is a very fascinating question because you could have distributed cameras everywhere, but even if you think from a single viewpoint, 10 microradians is a nice resolution for optics because 10 microradians is the resolution where you'll start to be limited by atmospheric effects. That's about a 10 centimeter aperture. If you go beyond 10 centimeters, you have to use adaptive optics. But you can get 10 microradians in a lot of atmospheric conditions with a reasonable aperture. Most optical systems actually currently are optimized for the resolution. That people don't usually worry about the large field of view. They try to get resolution. And a lot of optical systems at all scales get something very close to diffraction limited resolution. The point I wanted to make, actually, the reason for that, like with the image that I showed previously, was that we used an image system here that has pretty reasonable resolution, but has relatively narrow field of view. So this particular image was taken with a normal SLR camera mounted on a tripod that we scan, and this image is stitched together from several hundred snapshots to create the overall image. There's all kinds of things you could look at in terms of stitching quality. Could you find stitching errors in there? Almost certainly you could. But on the other hand, you look at that and you say, that's a pretty good image. And so it's not an image that was ever recorded on a single focal plane. But it is interesting to point out that it is possible to record this kind of image. And basically, if I give you an image with any kind of pixel count, if I can make an optical system that can hit the resolution for a certain aperture size, I can record images that would match that resolution over whatever field of view I want. The interesting question for you is going to be, can you do that in a simpler way than replicating the optical system or scanning it as a function of time? What you'd really like to say is, what is the maximum number of pixels you can get as a function of system volume? Okay, going back to the question of what is the total number of pixels you might like to get. So if you had 10 microradians and you go over a hemispherical field of view, just in sort of a nice resolution limit, you'd get 60 gigapixels as the kind of resolution that you'd like to see. Now you'd ask the question, how many spectral channels do you want? You can pick, based on design, over a wide range of the number of spectral channels you might like to measure. If you only say you want to measure 20 spectral channels, you're already up in the terapixel per single frame for cameras. Now, here's the interesting question. And then if you include time and all sorts of things, you're generating enormous data loads. There's nothing physically impossible about achieving this, making a sensor that can measure this kind of data. Well, I'll tell you some examples about how we might do it today, but it's certainly within the realm of physical plausibility that we can make sensors that measure this data load. And so the interesting question is, why don't we, and what will happen when we do? That we typically in sensor systems make a trade-off between the space we're going to measure over and the resolution we're going to measure over, and we do that to get the data load down. As information systems have evolved, that becomes less and less important. The example image that I showed you of the 100 megapixel image, I'm sitting here in a conference room. Actually, I'm using this. I'm not using CU's wireless for that. That was over Verizon Wireless, so it's a pretty crappy connection, and I was zooming that thing in and out. That's an existence proof that the information systems are there to do things with gigapixel scale images. So we see that more can be done than is currently being done. How much can be done and what we'll do when we get these kind of very large terapixel scale images, I think is just a fascinating question. How are you doing? All right, so why don't we have these high pixel count images? There's three basic reasons. One, which I've just talked about, is that this is a lot of data, so it's not clear what you're going to do. I think it's very clear that the information capacity is there to handle bigger images than we're handling so far, but how big we can handle and what will happen when we start to flood networks with this kind of data is unclear. But this one I think is reasonably resolved. This one I think is pretty interesting. So basically, you don't necessarily need to measure one detector element per resolved pixel element, but you need to get not that far off of that. You need a lot of detector elements to measure these things. what's happened with the continuing evolution of Moore's law and development of cell phone cameras is that the cost per pixel of optical detector elements has dropped from maybe $1 million per pixel 20 years ago to less than $1 per pixel today. So you can certainly, very commonly in cell phone cameras, you're buying sensors that are multiple megapixels for around $1 a megapixel. So at that price point, gigapixel imagers become very plausible, and then even terapixel imagers become plausible if you're the government or other large financial organizations. You expect, of course, that reduction in price will continue at least for another order of magnitude or so. So the idea of gigapixel or terapixel images in terms of can you buy that many pixels is very plausible right now. So the question is, can you build a system that can use these things to make a thing? And it turns out that currently optics may be the bottleneck. Can you make a camera that can really focus and capture very large pixel count images is a current bottleneck. Now, it's interesting to me, and I just, this is something that's just as obvious as anything, but it just wasn't something that was emphasized until recently. There's a very large literature in the consideration of resolution in optical systems, and most of it focuses around this idea of the Shannon number or the space bandwidth product. What is the number of modes that can come through an optical system as a function of aperture size? Basically, the space bandwidth product is going to be the aperture area divided by the wavelength squared. So this is known for generations and generations, and people really emphasize that it's not at all uncommon in optical systems to basically, if you take the Shannon number and then assign one angular resolution element per mode, you'll get the resolution. And it's very common, of course, for systems to hit diffraction limited resolution. It's very uncommon for systems to get anything approaching what would be the fundamental Shannon number in terms of the total number of pixels resolved in an imaging system. What the Shannon number predicts, these are numbers in megapixels, is if you're at a 1 millimeter aperture and you had like an f1 optic, you should be able to get 39 megapixels. If you go to f2, you might get 10 megapixels. The interesting thing is at the millimeter scale, you're not actually all that far off. The current demonstrated systems are certainly within an order of magnitude of the Shannon number in terms of their capacity. But when you go, to the centimeter scale, you should be getting a gigapixel at an f2 optic. If you go to 10 centimeters, you should be getting 100 gigapixels, according to this, fundamental limit of the space bandwidth product. You go up to, meter apertures, and you're well into the terapixel resolvable range. And this is just very far off of what's achieved in practice, which is, for an engineer, a very exciting thing because, often we're trying to fight things where we're close to the physical limit. Here, we have something where current systems are way, way off of what the physical limit should be. And so we have an opportunity to go and say, can we change that? Can we make systems that approach the physical limit? There are some very nice examples of gigapixel scale cameras around. This is the Argus imaging system that DARPA's developed. It does 1.7 gigapixels. It's a large system, half meter on a side, weighs a lot, gets the resolution with parallel arrays of cameras, but it is a nice demonstration. And one of the things that Argus has been very effective is in showing that information systems are capable of handling gigapixel scale images. Another one that's currently under development is the Large Synaptic Survey Telescope. Large Synaptic Survey Telescope. This is going to be installed in Chile in 2015. The camera is large. Here you see that this is just the inner. I think that's the inner camera part, and a person standing next to the camera engine, which sits inside the larger telescope. So the camera is the size of a small car. It's going to get 3.2 gigapixels. It's going to have dedicated fiber link to the supercomputer center in Illinois just to handle the data. It'll sample well over a terapixel data per night. Just to give you an idea what you can do with this kind of thing, the point of this telescope is to survey the night sky at a very rapid rate. So this telescope has orders of magnitude higher capacity than any previous telescope. I think the plan was to survey the night sky for the southern hemisphere 200 times over a 10-year lifetime. And I think if you look in the previous history of astronomy, what you see when you can capture a wide field is things that you would normally miss. That most of the night sky, for example, is unobserved. So in the previous history of astronomy, people have seen a few hundred supernovae. They expect to see around 1 million supernovae with this telescope. So you just, the idea that you can continuously observe everywhere in the night sky, and of course as we go to the very wide field telescopes that I'll tell you, or the wide scale imagers that I'll tell you about in a minute, you could image the whole night sky continuously. Who knows what you would see in the night sky if you had the capacity to look at the whole thing all the time. Another example of very large information capacity telescopes are lithographic lenses. So this is the history of lithographic lenses from 1984 at the top till 2004 at the bottom. Now these are analog imagers. They have to deliver a mask to a wafer for processing. And what you see is, from over this lifetime and trying to increase the information capacity to make larger and larger wafers. The thing you have to fight, the primary challenge, by the way, of making very high information capacity systems is Petzval curvature. This fundamental theorem of optics. As you go through light, as you go through lenses, the field will be curved, and so you can fight Petzval curvature by alternating positive and negative elements. So a lot of the design of this thing is really because in lithography it's necessary to get a very, very flat field. So these guys get very thick and involve lots of elements to get a flat field. But one thing that happens is what you notice with these systems is as you try to increase your field, we don't know what the fundamental limit is, but if you try to get diffraction limited performance over a larger and larger field, certainly the complexity of a lens system grows nonlinearly. And in the case of lithographic systems, this story actually ended in 1995, that the field size for lithographic systems has increased, but only by use of steppers, that the single exposure field size has not increased in the last 10 years. And that's because lenses just got to the point where it was no longer even conceivable to keep saying we're going to increase aperture size. People have got more intelligent processing, they've shortened the wavelength, but they haven't really increased field size in the last 10 years. Okay, so now let's talk a little bit about lens design and where the challenge comes in. Basically, so optics works using lenses. Imaging systems use lenses, and the lens is kind of analog processor that takes the world out here and creates a well-focused image of it. When you analyze lenses, and I'm sorry these are kind of faint, but here we just see a simple ray trace for a lens with various points in focus up here. We typically analyze these things by looking at the spot diagram. Shows where rays come in and where they hit in the image plane. And a lens designer comes up with all sorts of advanced optimization techniques to try to bring the spot diagram into tighter and tighter focus. The spot diagram is a measure strictly of geometric aberration. Has nothing to do with dispersion or diffraction at all. It's just so basically one assumes, typically in lens design, that if you can get the geometric blur down to somewhere in the range of the diffraction blur, the diffraction will dominate and you'll be in good shape. There's no point really in making the spot diagram a lot smaller than the diffractive blur. Lens design is scale invariant. So if I don't tell you the scale of this lens, then you wouldn't really know what these spots are. If I tell you what the spots are and I say now I'm going to make the lens 10 times bigger, the spot diagram will grow by a factor of 10 times as well. So what that means is that the diffraction blur for a lens is lambda times the f number, basically. That's the diffraction limit. And if I increase the scale, then I'll increase the geometric blur for that lens, but I won't increase the diffraction blur. And so increasing scale makes the geometric blur larger in comparison with the diffraction blur. You can see what that does to lens design. Basically, so this is a plot as a function of lens scale for what you would expect to see in terms of the total pixel count, the Shannon number for the lens, as a function for scale. And so this is a log plot. So this line is for the square. That if I start, typically we start with like a millimeter kind of scale where we think we can get something close to the megapixel of imaging. And then as we increase the scale, by a factor of 100, I would expect my total pixel count to grow by a factor of 10 to the fourth up to 10 gigapixels. So this would be if there was no geometric aberration, that the information capacity of the lens would grow as the square of the scale. Now these plots are saying, in this case, what if the geometric blur is initially 25% of the size of the diffraction blur? In this case, what if the geometric blur is 50%? It doesn't really matter. I mean, you end up at a different point in terms of total pixel count, but eventually geometric blur dominates for the lens, and so increasing the scale will no longer increase pixel count. So your options are to be happy with whatever pixel count you're going to get, or to change your lens design. So if you can say, well, I need to go to a more advanced lens design to get more pixels. This is just another way to look at that plot. I could take the information efficiency of the lens, which would be the potential Shannon number divided by the achieved Shannon number, and the information efficiency will fall as a function of scale. Okay, so you could say, well, what is the best you could do then as a function of scale? What happens in real systems? So if you don't have any diffraction blur, then as you increase, if you don't have any geometric blur, as you increase scale size, your information capacity will grow in proportion to the aperture area. Your volume, will increase as the aperture area to the cube, so that, or the aperture diameter to the cube. You have to make if you're just maintaining scale, the depth will remain. So it turns out that your pixel count, the relationship to the pixel count and the volume is that the volume will increase as the pixel count to the 3/2 power. This would be a lens with no geometric blur. There is one example of a lens that's known to have no geometric blur. Is called the Lumberg lens. It's a particular example of a Grin lens. So there is an existence proof that it's possible to make a lens without normal ray tracing geometric blur. And so this would be sort of the best that optics, that a focal system could do. Alternatively, you could use a holographic imager. So if you just said, I'm going to sense the field itself, then the system doesn't get any thicker as you increase scale size. You just need to increase your aperture area. This would be true of radar systems, but also true of optical holographic systems. That a holographic system should have pixel count, for a holographic system, the pixel count should grow linear, the volume should grow linear in the total pixel count. Now, this line is examples of what's really achieved in optical systems according to sort of our estimates. So we looked at this line and sort of made a speculation that in reality system volume grows as this, or that the system volume grows as the square of the pixel count, and then we set out to see if that was really true or not. And it can be better or worse than that, but that seems to be kind of an empirical thing. Our thinking about that started with some work that came from Adolf Lohmann in 1989. Basically, as you increase scale, but you want to maintain diffraction limited performance, what's typically done is that you increase your F number, so make the system thicker, and you decrease your field of view. Okay, so those two things will tend to maintain diffraction limited performance even as you increase aperture size, but they'll tend to reduce your pixel count. So we have a program. Well, and let me, before I say this, the idea of increasing the F number as a function of scale was what Lohmann suggested in an empirical law in his paper in 1989. What he said was that empirically you would observe that the F number increases as the 1/3 power of scale. And so if you go and look at common systems, it's not a hard and fast rule. It depends how hard you want to try. If you make your lens very aggressive, you can violate this empirical law. But as a matter of sort of demonstrated systems, it does seem to be kind of true that F number increases as the 1/3 power of scale. What we did was develop a optimization program for lens design. This is some work that a student named Nan Zhang has been doing in my lab. Lenses are just a fascinating, beautiful thing to think about. And lens design is very relatively simple. Over the history of lenses, there's really only 5 or 10 basic lens designs that account for almost all optical systems. What Nan has done is use something called paraxial ray tracing, where he goes and has a program that can algebraically expand surfaces in a lens system, and then use a polynomial optimization to automatically optimize ray tracing systems. It only works for relatively simple lens systems, but it works very effectively for these lens systems. So Nan used his program, for example, with a plano convex lens. So he has a front planar surface and an aspheric back surface. And then he goes and he says, all right, I want to optimize for the largest field of view that I can see as a function of f number, as a function of scale. This is the plot for this optimization. Actually, the lower plot is for a spherical surface on the lens, and the upper plot is for an aspheric surface on the lens, and then just optimizing f number and field of view. And what you find, of course, is you increase aperture size, both the field of view and the f number will drop. F number and field of view can be translated into system volume and Shannon number. If I tell you the f number and the field of view, I can calculate what the Shannon number and the volume is. So you get a surface like this, which is a function of, as a function of aperture size, in this case going from a millimeter out to a full meter, of what the system volume is going to be and what the Shannon number is. And then you can sort of say, what's the minimum volume as a function of Shannon number across all scales? And you can make a plot like this. This is sort of projecting that three-dimensional, or the three-dimensional surface onto this volume thing, and then you look at this curve, which is the minimum volume as a function of Shannon number. And so, for example, for this, once you pick a lens design, you can get a scaling law. What is the information capacity as a function of volume for that lens design? And so what we find for the plano convex lens is that the system volume grows as the fourth power of the Shannon number. And then just as a next step, we looked at a biconvex lens with the same kind of optimization, same kind of plots, and we're able to show that for that particular design, that both the field of view and the f number are going to have to collapse, and the system volume will grow as the square of the Shannon number, which kind of confirmed our idea that for simple lens systems, volume has to grow as the square of the Shannon number. But it's an interesting area for all kinds of research. We do know the limits, basically, that if you had a perfect lens, you would grow as the 3/2 power. Now, in practice, you're going to grow probably slower than the 3/2 power because there's a sort of manufacturing cost of lenses. So at small scales, basically, relatively simple lenses will make sense. At large scales, you're going to make more and more complex lenses, which would also be high performance at a smaller scale, but they're not economically viable. There's no economic reason to make them at a smaller scale. At larger scales, we make more and more complex lens systems. Okay, so what we want to do, first of all, we just want to solve this challenge of saying we want to get optics that will deliver a very high Shannon number in the minimum volume that we can get. There are potentially many strategies that you might pursue in lens and optical system design. To do this, the three that we've looked at are looking at Grin lenses, which are known to have the Lumberg solution, at least for making a very high quality focal plane. Then I'm going to tell you a little bit about multi-scale lens design, which is a lens design strategy that we've been focusing on for making very high information capacity lenses. And then another strategy is holographic imaging, which basically says, punt, get rid of lenses altogether, and life would be good. So I'll comment on each one of those three strategies. I only have this one slide on Grin systems. So the Lumberg lens was proposed by Lumberg in the mid-40s. Basically, came up with a particular index distribution, which has the property that it focuses on a sphere. So if you're willing to focus on a sphere and can manufacture a sphere that has exactly the index profile called for in the Lumberg lens, you have a lens with no geometric distortion. That's fantastic for many reasons, but mostly fantastic because it's an existence proof that it's possible to make this kind of lens. It's an amazing thing about the universe that light focuses at all, right? That obviously it's important to us that we can see images. Isn't it surprising that all these approximations we use in optics work out and we're able to form images? But not only can we do that, but we can get away with a lot of the assumptions we make in conventional optics if we have a Lumberg lens. This is actually I saw some interesting work today in Dr. Park's lab about invisibility cloaks. This is from our metamaterials group at Duke, led by David Smith. He's been working on Lumberg lenses in two-dimensional microwave materials and has demonstrated that using transformation optics you can take a Lundberg lens and flatten it, so that instead of having a spherical focus it'll have a planar focus. So I think that's an interesting thing, and there's a lot of things you could do with GRIN optics if you can figure out how to manufacture them. We're currently in our program focusing on what happens if we use conventional surfaces for lens design. All right, so another option would be holography. So you could imagine making gigapixel holograms. We actually are working on a project with Jim Feenup at the University of Rochester, where the goal of the project is to form gigapixel digital holograms. It does seem to be, so actually we're limited currently by information capacity. We have manufactured 100 megapixel kind of scale holograms in the lab. I find this one very fascinating actually, because you could ask yourself, why isn't holography more useful? You know, the laser is 50 years old. When we flash illuminate a scene, we flash illuminate with white light. Why don't we flash illuminate with laser light? And it turns out that you know, if you, from a fundamental you know, SNR information capacity, that holograms are very competitive with conventional imagers. That if you flood a scene with light, capture it with a hologram, the SNR should be, you know, very, very similar. Actually, I think that personally, I think that the boundary is moving. That there will be more holographic imaging. We're not ready, maybe yet, for sort of you know, holography replacing replacing conventional imaging. But as lasers become, actually, I think the number one thing that's held holography back is that the cost of laser photons is higher than the cost of incoherent photons. But as lasers become, you know, cheaper and more effective, you may well imagine systems where you would use laser flash. And interesting things about holograms is, first of all, you get very flat, potentially very high pixel count imagers, and you can get three-dimensional measurement. Now, I want to just tell you about an example of holography from our lab, because one, it shows sort of some of the exciting opportunity of holography, and then it also shows, I think, what's the killer challenge of holography. I've taught optics for a long time, and I always liked this question. I always would go into a class and say, you know, is a hologram a two-dimensional object or a three-dimensional object? And for the last, you know, 20 years, until like last year, my answer was that a hologram is a two-dimensional object. That a hologram, first of all, it's like you captured a window. You know, that the light that was on this two-dimensional plane is captured in the hologram. You can look through that window any way you want. You can see the object as if it was there, but the window is a two-dimensional object. So the hologram that you captured is two-dimensional. So I was very surprised last year when I changed my mind about that. I no longer believe that to be true, that a hologram actually is a three-dimensional thing. The difference between holograms and other forms, holography then is normally separated from tomography. Tomography is a true three-dimensional imaging approach that gives you the object from multiple directions and allows you to rotate and examine the object in 3 dimensions. You know, I'm not going to go through the full details today, but the window that you capture with a hologram is actually a slice of the 3-dimensional Fourier transform of the object. And knowing that that's a slice and using constrained optimization, it turns out that you can reconstruct a 3-dimensional object. And now, more than that, you know, I think one of the defining features in holography is the distinction between Gabor holography and Lisi-Packnick holography. Lisi-Packnick holography used communication theory to say, when I record a hologram, I have a reference and I have a signal. I need to put the signal on a carrier in some way that allows me to separate it out. So the problem with Gabor holography was that the reference and the signal were not easily separable, and in Lisi-Packnick holography they were. Currently, I believe that that's not that big a deal either, that it turns out that we can separate the background terms from a Gabor hologram from the signal, also using constrained optimization. Basically, this, you know, in any imaging system, we have a forward model that describes the mapping from our signal to our measurements. We have noise. We've been doing a lot of work on this idea of compressive measurement, which basically says that I can, you know, basically over the last 10 or 15 years, we started with the ideas of signal regularization, where I could do denoising and compression on signals. And once you think, well, if a signal is compressible post-measurement, maybe you made too many measurements, you start to think about, could you multiplex measurements and estimate the signal with fewer amounts of data, that somehow your measurements should reflect the true information capacity of the signal. And also, if it's possible to denoise a signal, it should be possible to make a noisier measurement and still get the signal. And that's effectively what we're doing with compressive measurement. We take our forward model, which would be a mapping from the field. This is G is equal to H times F. And we apply a constraint to the signal, which usually is a sparsity constraint on some basis, or a sparsity constraint on the derivative of the signal. Now in this case, the object that we're looking at with the hologram are dandelion seeds, which have the nice property that they're kind of sparse. And I'll talk about the importance of that in just a minute. They're kind of sharp, high-frequency objects that are kind of sparse. This is some results from a paper we had last summer. We measure a single exposure, a Gabor hologram. The object is a couple of dandelion seeds separated by a few centimeters. We apply constrained optimization to the three-dimensional data cube of the object, and we were able to separate and image the dandelion seeds separately in their own range bins from a single exposure. So we get a true three-dimensional reconstruction from a single two-dimensional measurement, and we're able to isolate the lower frequency Gabor terms in the z equals 0 plane, while we get the high frequency terms in their known range bins. This is for comparison. This is the constrained optimization reconstruction. This is if we just do take the measured field and back propagate it through the volume. So what you see is sort of a mess everywhere. This is a three-dimensional rendering of the two different planes reconstructed. Okay, so this is basically pretty fantastic. It's a diverse space. It may work that you might want to measure a wide variety of different projections. We have kind of not very good Z resolution. Our Z resolution was about 1 centimeter. Our resolution is determined by the solid angle still that we capture. We have done, actually I have, if you're interested, I have small plots of microscopic versions of this where we have a large numeric aperture where we can get micron scale Z resolution. You can also do this on multispectral recording. If you use reflection geometry multispectral, you could get very high Z resolution. All right, so that's one aspect of holography. And I do believe it's an unanswered question. I mean, the one thing you could also do with compressive holography is you could put a bunch of sensors around the plane and not densely populate the plane and still reconstruct, a very high resolution two-dimensional image. There was a trick, though, in that data that the object was sparse in the observed basis. A lot of work in compressive imaging works with most images. If I look around the room, this is not a sparse scene. It's compressible because it's sparse on like a wavelet basis or something, but it's not sparse in a native basis. That works great with incoherent imaging. With holography, you have speckle, so that if I image this scene holographically, I would take every point in the space and multiply by random phase. What that means is that a scene which is sparse in sort of its intensity basis is not sparse anymore after I multiply by random phase. And so typical scenes that are coherent are not really sparse on any basis. So this was a problem for us with compressive holography, that we actually couldn't, the approach wouldn't work if we had a scene that wasn't sort of sparse in its native basis. So we looked at ways to deal with that, and I'm going to go kind of quickly through this because I want to tell you a little bit about multi-scale design as well. So this is something more typical. We have some letters in plastic at different ranges. We see the diffraction pattern. You see speckle on top of the letters because it's just rough plastic. Now in this case, the object field is random. We assume it's a Gaussian random process where basically the real and imaginary parts. The density of the object, the magnitude of the object at any point, has a non-zero, meaning the object has a non-zero scattering variance, but the mean value of the object is 0. What we'd really like to measure, the interesting thing is, what we'd really like to measure is not the we don't really care about the object field. We want to know the object, the underlying scattering density, and it turns out we can make a forward model on that, on the underlying scattering density. That what we do is we take the measurement from the object to the field, and what we did is we back propagated into the three-dimensional volume. So we take our two-dimensional measurements, we back propagate into the three-dimensional volume, and then we average that over many exposures. So in some sense this is compressive measurement because we're using a finite two-dimensional space, but it's not compressive in the sense that we're making 50 exposures more or less of the same scene to get a representation of the speckle field. And then we have a forward model that maps the scattering density onto the expectation value of the back propagated field. And the interesting thing is that actually the condition number of this average thing is higher than the condition number of the direct measurement, where the direct measurement was a mapping from 2D to, or from 3D to 2D and had poor conditioning. After you do this averaging, you get a better condition mapping from 3D to the sort of 4D average space. But then we treat this the same as we do compressive measurements, that we try to do, we combine linear regression, minimization of the L2 scattering density with the L1 minimization. From an SNR point of view, this turns out to be equivalent to incoherent imaging. Basically, this is what we're doing here is the same as we're taking multiple holograms and averaging them, so it ends up to be equivalent to incoherent imaging, with the only advantage being that we don't have lenses, so that we were able to form an image with it without lenses. We do this convex optimization again. So here's some experimental results. This is measure a hologram and back propagate it. You see some letters. This is back propagation averaged over, I take 50 fields, back propagate them all on average, and you see the speckle reduced, but you still see the image reconstructed. So these are all separated by a centimeter or so. Each of the letters is at different range bins. And so these are these slices. So this is 5 or so millimeters on a side, and here we've gone from 5. These planes are separated by about 5 millimeters in the different reconstruction depths. Here, when you use the constrained optimization, we still have some crosstalk between the different planes, but we do a much better job at localizing the letters at their respective range bins. So I think that's all. Yeah, I mean, well, this was these two are just different regularization parameters in the algorithm, so one does better than the other. Oh, and then this one's fun just because we separated the word ladybug at one range bin from an actual ladybug at a different range bin. Which, the nice thing about that is just showing that we can holographically reconstruct regular objects, that you can take regular scenes and form nice holographic reconstructions of them. I think that you will, digital holography, basically the underlying feature that's driving all these systems is the availability of lots of detector elements. A fundamental challenge with holography is the need to distribute a reference. So that, I think that's the main thing that makes it so that we can put together very large arrays of detector elements and we can reconstruct them holographically. The challenge of figuring out a very nice way to distribute a reference to all those planes is probably a major factor holding back holography, but that's certainly a resolvable technical challenge. That there are diverse ways you could think of coupling a reference effectively into a detector plane, and also interesting strategies for referenceless holography that I think we'll continue to develop. So I personally, said something about holography here, but the issue of why regular imaging is used in some cases and holography is used in other cases is not clear. I do think, we were looking at microscopy today that, especially in microscopy, holography will make dramatic bounds. And you can, there's some very nice work already, I think, in lensless microscopic holography, where it will be very competitive with normal imaging systems. Okay, so we have these two strategies. We're trying to get number of pixels way up. One strategy was grid lenses, one strategy is holography. Another strategy is just sort of to observe. I got this big optic. It's collecting a lot of light. Typically when I make the optic big, I only look at the light at the center of the field. Can't I do something? Couldn't I put optics out here that would correct this field in some way? And this is sort of based on the idea that saying that, well, lens at a small, basically lenses at small aperture size are better than lenses at big aperture size, that they're more effective at getting a higher information efficiency. Given that that's true, could I manufacture correctors on the smaller scale that would process the field to get back the resolution that I lost from the larger optic? That does turn out to be possible. There's some there's precedence, of course, for working with multi-aperture lens systems. One that's Christensen and Haney looked at using multi-scale kind of designs for optical interconnects for very similar reasons. There's this planoptic camera, which uses lenslets in the back plane to try to get sense the radiance function and get three-dimensional imaging. This is another example of a planoptic camera. The Tombow camera uses parallel sampling to try to use digital super resolution. So what these systems have really shown, and then this is our own work on the montage program where we built the infrared Tombow style camera, and we were able to reliably show about 3x digital super resolution, effectively making smaller pixel size. This results from montage showing a conventional night vision camera and what we would get for a montage reconstruction. We didn't quite hit exactly the resolution of the digital system, but we were a factor of 7 thinner in the montage system. And if you look at, we definitely did dramatically better than what you would get from a single lenslet. This would be the image we get from a single lenslet. This is what you get processed over multiple lenses with digital super resolution. Basically coming out of montage, we said, well, what we've learned is that we can manufacture very, very high quality. In these small scale lenses, first of all, work better relative to the diffraction limit and have, effectively, as a function of scale, less geometric blur. They're also much more manufacturable, that I have manufacturing technologies that will make very sophisticated compound small scale lenses. Can I use those compound aspheric manufacturing process with small scale lenses to correct issues that I may have with a larger scale objective? So we did this design study last year for a relatively small aperture, an 8mm aperture, comparing conventional a conventional lens optimized for a planar surface, conventional lens with a spherical surface, and then some multi-scale designs. And we were able to increase the pixel count, the number of resolvable spots we get for the lens by order of 50 or so with a relative to the conventional planar surface, and a factor of 3 or so relative to a conventional lens where you assume the conventional lens has a spherical focal plane. Now, of course, one of the advantages of this multi-scale design is that you get huge advantages in an imaging system by just having a spherical focal plane. But spherical focal planes are difficult to manufacture, so you could, at first level, just think of the multi-scale design as an effective way to use small, flat optics to manufacture a spherical focal plane. This is a more recent design using a Heliar lens. And in this case, we got up close to 100 megapixels. We're, basically, as Professor Feiston noted, we're just at the start of a DARPA program called Mosaic, where if you go Google Mosaic online, you can see what the specs are, but we promised DARPA that we can make a 50 gigapixel camera. We did, actually, if you get into the details of that design, that's not likely to be a single aperture 50 gigapixel camera. We're more like a 10 by 10 array of 5 gigapixel cameras, which is sort of easier to achieve. But actually, it's a very fluid area. There's a lot of different designers that are working on this kind of stuff, and we're pursuing a lot of designs. Basically, and here's kind of the take-home message of one way to think about this. If you look 30 years ago, and there's a lot of similarity between what's happening in optics and what happened in the development of microprocessors. 30, 40 years ago, people tried to make single supercomputers that were vector computers where everything was processed through a single processor. That model broke down as microprocessors got better and better, and the cost of microprocessors collapsed. So now if you want to make a supercomputer, you do it from arrays of, you make a supercomputer from arrays of microcomputers. Basically, we think the same thing is going to happen with optics, that we're going to make cameras that will look like this, where we have all these segmented micro cameras on the back. So an overall camera would look like this mosaic of lots, thousands of small cameras integrated together in the backplane. So these are just some mechanical drawings of some of the cameras that we're working on in that regard. Obviously, there'll be some very interesting alignment and fabrication issues in putting this thing together. But Actually, the guy who's in charge of the mechanical alignment of this thing is Jung-Seng Kim, who was also, was one of the developers of the Lambda router at Bell Labs. And the Lambda router was a 1400 by 1400 or something optical cross-connect, which encountered very similar kinds of alignment and integration issues to what we expect to encounter in the Mosaic camera. Thanks very much for your attention, and I'm happy to answer any questions that you may have.
So your multi-lens system, is it a coherent system, or you just forget about diffraction limit and just stick to a diffraction limit for small aperture?
No, you have the diffraction limit is determined by the large aperture. You have the resolution of the large aperture.
So it's all phased, like stay in phase?
It's not necessary for the micro cameras to be relatively phased relative to each other.
So you are losing diffraction resolution for a bit?
No.
No, you can't have both.
Yes, you can.
You have to phase it.
No.
No, okay.
You're wrong. Imagine that I have a large, this is a telescope, right? A typical telescope has a large objective and an eyepiece. The resolution you achieve is the resolution of the objective, even though you're looking through a small eyepiece.
Well, if you break the eyepiece in 100 small pieces.
No, but if you have the same size of the eyepiece, but you replicate 100 eyepieces, you maintain the resolution of the large objective. So there's no coherence relative. These are well-formed images on the backplane. They don't have to be coherently combined.
In the averaging with the holography, you're taking the multiple images to overcome the speckle. Is there something changed image to image? I missed a key detail there. Why don't I just get 50 images of the same speckle?
We changed the illumination angle by a very small amount.
That's what I missed. Thank you.
How that changes the speckle dramatically is a fascinating question, but it does. Yeah.
I think you mentioned earlier that we're getting to a point that where coherent imaging images can be as good as coherent images. Do you think they can, as far as the SNR goes, do you think they can be better? Like doing hand detection, like doing and that kind of thing done with.
No, it's an interesting question that Kelvin and I were sort of talking about in an oblique way earlier. Both of them can get to the shot noise limit, and neither of them will get better than the shot noise limit. I guess that's an interesting question. Well, basically, coherent systems can be better for the following reason. For an incoherent system, you have to know what you're measuring. So if you have one spot and you're measuring it well focused in a coherent system, you'll get the shot noise limit, or an incoherent system, you get the shot noise limit. In a coherent system, you don't have to know where the spot is. So you can have an unknown distribution of sources in 3 dimensions and get the shot noise limit on all of them without any prior knowledge. And so to that extent, a coherent system is better. But that's really just another example of, because you don't need a lens, you don't need all the priors of the lens, you won't have aberrations, so you may do better. But especially, I guess, for 3-dimensional sources, a coherent system can get arbitrary depth of field without any SNR cost, where I don't think you can do that for an incoherent system.
Is it safe to say that the optically observed hologram is 2D and the digital hologram could be?
No, I don't think so, because a hologram is a 2-dimensional object, right? But it contains information about the 3-dimensional nature of the source. The hologram is a slice of the 3-dimensional Fourier transform of the source, and so whether it's recorded optically or digitally, if I have an optical one, I could go and analyze it and figure out as well. Basically, I can digitize it, I would say.
You cannot do the optimization with your eye.
I don't know, maybe I wouldn't, somebody, but actually I think people do actually. When you look at a hologram, you are able to interpret the 3-dimensional structure of the object. So you are effectively doing 3-dimensional processing.
So if you
Absolutely, sure.
So I don't quite understand the distinction. Both incoherent and coherent two-dimensional images can contain three-dimensional information, but they're both just two-dimensional images.
That's true. So you're recording two-dimensional data, and I think it is, and I'm not saying that it was never thought of before, but there has been an implicit assumption of that dimensionality was conserved, kind of. That tomographic images measure three-dimensional data so they can reconstruct three dimensions. What you're saying is absolutely true, and what the resolution we get in 3D is the same as what we would get if we were doing depth by defocus with the hologram. Our SNR is better, though, than it would be from depth by defocus because you know, that we don't have the background from the defocus planes, really. And so I don't think, I mean, what you would have here is the same as the kind of three-dimensional resolution you would have like with a rotational shear interferometer for an incoherent system. From an incoherent image, you know, if I just recorded an incoherent image without doing any defocus, the coding there is going to be very bad for doing three-dimensional reconstruction. Unless I use Raphael's rotating PSF.
You can't resolve the occlusion if you don't see it.
I'm sorry?
Occlusion?
Oh, sure. Yeah, you can't see, where you're not getting light, you can't do anything, sure.
Well, with tomography, if you have multiple views.
Well, yeah, if you can see around things, yeah. I mean, but I think that what I showed you is kind of an extreme example of single-frame three-dimensional reconstruction. There is a lot of work, of course, on compressive tomography in addition to this work. So it's certainly measuring the full data cube is probably overkill in tomography. That you need to look behind, but as you get more angles, you probably don't need all those angles.